You think you know what black is, but if you orbited a black hole, you'd discover that the darkest object in the universe is surrounded by the brightest, most twisted light show you've ever seen. Stars would appear in impossible places, time would stretch like taffy, and you'd see things that shouldn't exist, including the back of your own head. This isn't science fiction. This is what Einstein's equations actually predict you'd witness on the most dangerous sightseeing trip in the cosmos. Let's start with what you're actually looking at when you approach a black hole. First, forget everything you think you know about black holes being invisible. That's only true if you're looking at a lonely black hole floating in empty space. But most black holes aren't lonely. They're feeding. Picture a cosmic whirlpool, matter from nearby stars, gas clouds and debris spirals inward toward the black hole, forming what astronomers call an accretion disk. This disk is blindingly bright, hotter than the surface of the sun, because as matter accelerates toward the black hole, friction heats it to millions of degrees. It glows white-hot in the center, fading to red at the edges, like a cosmic stovetop burner. But here's where your journey gets weird. As you approach this system, you're not just dealing with normal physics anymore. You're entering a realm where Einstein's general relativity takes over, where space and time themselves become twisted by the black hole's immense gravity. A black hole with the mass of our sun would create an event horizon about 6 kilometers across. But the supermassive black hole at the center of our galaxy, 4 million times more massive than the sun, creates a gravitational field so intense that it bends light itself. Think of spacetime like a stretched rubber sheet. A bowling ball placed in the center creates a depression. Roll a marble nearby, and it curves around the depression. But a black hole isn't just a bowling ball. It's like a bowling ball so heavy it punches a hole clean through the sheet. And when light tries to travel near this hole, it doesn't travel in straight lines anymore. It follows the curves of warped spacetime. Now imagine you're in a spacecraft approaching this black hole from a safe distance. At first, everything looks normal. You see the bright accretion disk, maybe some jets of material shooting out from the poles. But as you get closer, something extraordinary starts happening to the light around you. Let's use a specific example to make this concrete. You're approaching Sagittarius A star, the supermassive black hole at our galaxy's center. It has a mass of 4.3 million suns and an event horizon, the point of no return, about 12 million kilometers in radius. That's about 1/6 the size of Mercury's orbit around the sun. As you approach from, say, 10 times the distance of the event horizon, you start to notice the first weird effect: gravitational lensing. The black hole's gravity is bending light from objects behind it, acting like a cosmic magnifying glass. Stars that should be hidden directly behind the black hole become visible as bright arcs of light curving around its edges. But that's just the beginning. As you get closer, let's say 3 times the event horizon distance, you start to see something that shouldn't be possible. You're looking at the accretion disk, which should appear as a flat, spinning disk when viewed from the side. But instead, you see what looks like a bright ring completely surrounding the black hole. You're seeing both the top and bottom of the disk simultaneously. Here's how this works. Light from the far side of the disk travels up and over the black hole, gets bent by gravity, and curves back down to reach your eyes. Meanwhile, light from the near side of the disk travels under the black hole, gets bent upward, and also reaches your eyes. The black hole's gravity is so strong, it's literally showing you the backside of things. This creates what scientists call the photon sphere, a region where light can orbit the black hole. The bright ring you see isn't actually a single ring, but rather the combined effect of light taking different paths around the black hole. Some light travels directly to you, while other light takes longer paths, curving around the black hole before reaching your eyes. This creates the complex, layered appearance of the ring structure you observe. As you continue your approach, now just twice the event horizon distance, the visual distortions become extreme. The accretion disk no longer looks like a disk at all. Instead, it appears as a complex, swirling pattern of bright and dark regions. Parts of the disk that are moving toward you appear blindingly bright due to something called relativistic beaming. The light gets compressed and amplified. parts moving away from you appear dimmer and redder. But here's where things get really interesting and really dangerous. Everything I've described so far assumes you're somehow hovering at a fixed distance from the black hole, fighting against its gravitational pull with impossibly powerful rockets. In reality, you'd be falling, and when you're falling toward a black hole, what you see changes dramatically. First, there's the issue of time dilation. As you fall deeper into the black hole's gravitational well, time itself slows down relative to the outside universe. From your perspective, however, your own time feels normal. What changes is how you see light from the outside universe. As you fall inward, light from distant objects gets gravitationally blue-shifted, compressed to higher frequencies and energies, making distant stars appear brighter and bluer. But there's also the Doppler effect from your motion. As you fall inward at increasing speed, light from objects in your direction of fall gets blue-shifted even more, while light from objects behind you gets red-shifted. Near a black hole, this Doppler effect becomes so extreme that it can dominate over other effects, creating a complex pattern of color shifts across your field of view. Then there's the issue of what happens if you're not alone. Let's say you're orbiting a binary black hole system. Two black holes spiraling around each other. NASA has created visualizations of exactly this scenario, and what you'd see is like a cosmic funhouse mirror. Each black hole acts as a gravitational lens for the other's accretion disk. As one black hole passes in front of the other, its partner's disk appears to stretch and distort into rapidly changing arcs and crescents. The visualization shows two accretion disks, one colored red, one blue, to make the distortions easier to track. As you watch, the blue disk appears to wrap around the red one, then stretch into impossible shapes as the black hole's gravity fields interact. It's like watching space itself get twisted into knots. But perhaps the most unsettling effect happens as you get very close to the event horizon. Due to the extreme bending of light, you start to see things that violate your basic understanding of geometry. Looking directly away from the black hole, you can see the entire outside universe compressed into a bright ring. Looking toward the black hole, you see more of the outside universe, because light from behind you has been bent around to reach your eyes. In the most extreme case, if you could somehow survive the journey, you might even see the back of your own head. Light leaving the back of your head could travel around the black hole and return to your eyes. Of course, this is purely theoretical. The tidal forces would tear you apart long before you got close enough for this effect to occur. So why does any of this matter to you sitting safely on Earth? Because understanding what you'd see orbiting a black hole isn't just about satisfying curiosity. It's about testing the fundamental laws of physics and understanding the most extreme environments in the universe. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, they were looking for exactly these effects: the photon ring, the gravitational lensing, the way light behaves in extremely warped spacetime. That image of the black hole in Galaxy M87 confirmed Einstein's predictions with stunning accuracy, a century after he first wrote down his equations. But there's a more immediate connection to your daily life. The GPS system in your phone has to account for time dilation effects. The fact that time runs slightly faster for satellites in orbit than it does on Earth's surface. This is the same physics that creates the extreme time distortions near black holes, just much weaker. If engineers didn't correct for these relativistic effects, your GPS would be off by miles. Understanding black holes also helps us understand the structure of the universe itself. These objects are the engines that power quasars, the brightest objects in the cosmos, visible across billions of light years. They regulate star formation in galaxies, determine how galaxies merge and evolve, and may hold clues to the ultimate fate of the universe. And here's something that might keep you up at night. Astronomers estimate there are roughly 100 million black holes in our galaxy alone. Most are stellar mass black holes formed when massive stars collapse. But there are also intermediate mass black holes and the supermassive monsters at galactic centers. We're living in a universe filled with these space-time warping objects, and we're only just beginning to understand what they do to the fabric of reality itself. So here's what you'd actually see orbiting a black hole. Not the simple dark circle you might expect, but a complex light show created by gravity itself. Bright rings of twisted starlight, accretion disks that appear to wrap around impossible geometries, and the entire universe compressed into patterns that challenge your basic understanding of space and time. The darkest objects in the universe turn out to create some of the brightest and most beautiful phenomena we know. And the next time you use GPS or look up at the night sky, remember, you're experiencing the same physics that creates these cosmic mirages, just scaled down to a level that won't tear you apart. Einstein's universe is far stranger and more wonderful than our everyday experience suggests, and black holes are the places where that strangeness becomes impossible to ignore.